Welcome to ECE113DA. My name is Mike Briggs. I'm the instructor of the course. We have two TAs, Jiawei Zhang and Ushasi Ghosh. Jiawei will be handling the Thursday lab at 3 p.m. Ushashi will be doing the 9 a.m. on Monday lab, and they will be swapping back and forth on the Monday 3 p.m. lab. So for this week, I'm going to be talking a lot about the course information, what the course consists of and some of the policies and things like that. We'll also be talking a little bit about, what the actual course is. What are we talking about with this course? We'll be asking and answering, I hope, the question, what is DSP? We'll be talking a little bit of theory, things that you might have learned in 113 on waveform generation and aliasing. I'll probably give some comments on what I'd like to see in the write-ups on the labs. And then, actually not part of this lecture, but as part of the first part of your lab sections, you will be given a lecture on more of the nuts and bolts of how to actually conduct the lab. Okay, so for office hours, go to the main page on CCLE. We've all three posted our office hours. I would say that for me in particular, if you cannot meet at the times that I've specified, I have one for 8 p.m., I believe, so that would be accommodating, I hope, to the people on the other side of the earth. But if not, they don't work for you, just let me know and we can set up another time. So there will be new handouts and things like that on CCLE. I would like you to check CCLE often for those kinds of things. And this is important. Set your email clients to flag my emails. You can do that. Every decent email client these days has the ability to flag emails from certain sources, and you should do that for all of your instructors. You really don't want to miss emails from instructors. I know you guys get a lot of emails, and it's hard to keep them all straight and all of that, but gee, many Christmas, you really got to be able to read and understand your instructors' emails. You really need to do that. So do this. Okay, on course evaluations, so these are the surveys, the evaluations that you fill out, 2 for each quarter, and turns out that for the A and the B sections, there will be evaluations for each, and there are 2 evaluations, one for the instructor and one for the TA. So do that. And I do read those evaluations. I always am looking for better ideas that will better help improve the course. Those are what I'm looking for. So this is another general item. You probably know this by now, but I'm just making sure that you're aware of it. There is a campus-wide MATLAB license now. All you have to do is to go download it, so you can have a good copy of MATLAB on your own device. And we will be using it from time to time. So I would advise you to do that, to download it to your laptop or your device, because we will be asking you to use it. Okay, so we want you to assign teams, and I'm talking mainly about 2-person teams. Under certain conditions, we go with 3, not for the labs, but maybe there's one that will grandfather in. But for the project, especially for the long project that starts in week 9, we will allow 3-person teams. The project that the 3-person team takes on needs to be sufficiently challenging. And we want to assign these randomly, so we will be assigning them randomly. Again, except for one team that is grandfathered in. So remember how it worked in ECE3. Basically, the teammates that you ended up with are the ones that sat next to you when you walked in the lab on the first day. It's not going to be quite that way, obviously, this time, but something like that. So one of the cool things about this course is that you get to choose your own project. Within, certain constraints, of course, but yeah, you're going to get to choose your own project. We're going to post a list of thought starters. Again, there's already one team that's indicated some things that they would like to do. You can choose a project that is not on the list, and that's fine. Again, one criterion is that it have a strong component of digital signal processing. But there are a couple of other things depending on the project that you choose. Things that we'll be looking for. Again, sufficiently challenging. Of course, we will be, and by we I mean the TA for your lab and me, we will have to approve your choice. When you pick a topic, you're going to be doing your own research, meaning that you're going to be studying up that project and implementing the ideas that you find when you do that studying. And you are going to set the goals. So that means you're going to decide if your results are reasonable. Another cool thing is that we will have what I call BDML projects, which are those are big data machine learning projects. So that is, you will, if you choose to use one of those projects, you'll be creating an AI entity of some kind using, I call it a BCS, a big computer in the sky. We're not going to ask you to train an AI entity on your laptop. That would just take forever. And so we're not going to do that. Use a lot of the tools that are out there, the Google I'm blanking now on the Google something. Anyway, there are others also, and Scikit Learn and things like that. But the AI entity that is created, basically meaning a bunch of coefficients and things like that, that will be installed on an embedded system. And this is a new embedded system, an H7, that is supplied by ST Micro H7. So here's yet another cool thing. This is a radar board, and that's about life size, actually. It's not very large at all. The antennas are right here. Here are the antennas, and we have software for that. It's a Texas Instruments product, and you'll be using Code Composer Studio and another software if you choose to do some radar work. So that is one of the possibilities. We've had certain levels of success using the radar in two previous times that we've used it, and I'm always looking to see if we can improve on the way things are going there. I do have a couple of ideas, some things I'd really like to try, so if somebody wants to get into radar, man, that'd be great. We have just the one unit. We're going to try to keep the project fairly simple, but there is a ton of DSP in radar work. Let's see here. So here's, this is the board. This is the embedded system that we'll be using. It's an STM32, ST Micro STM32. This is a brand new initiative. It's the first time, this quarter is the first time we will have used it. And you know what that means? That means you are the guinea pigs. We will be learning along with you. We do have a fair amount of knowledge about how to use this thing, but we will not have the answers to all of your questions. Sad to say, but that's the way it is. You know, every time we use it, we learn more. But still, this is promising to be a very cool and rewarding system to be working with. It is a fairly sophisticated, very sophisticated, fairly fast product. It does not have a DSP core like what we've been using before. But it does have some specialized DSP instructions that do make it run faster than it would normally. So we're going to see how this goes, and we fully expect that this is going to be a highly successful venture. So there's one thing about all of this, being able to choose your own topic and all of that, is that you can't expect the TA and me to be expert in your chosen project. You know, there are just too many of the different kinds of projects. Obviously, some of them we've seen before, and we have always some general solutions, but maybe not directly related to your project. So you're going to be doing the literature search. You're going to be applying what you learn to your project. We should be able to help on things that are related directly to the DSP development environment. That's where, you know, you should expect answers from us, and we hope that we will have them. If we don't, we'll be off looking for them and going to other experts that are around and stuff like that. Okay, so the lab reports are going to be due at 11:55 p.m. the Saturday after the lab. So the Thursday people, you've got Friday, but you know what you've got is Saturday to get the lab done. I decided that it's just best, even though one's on Thursday and the other two are on Monday. During the week, you're probably not going to have that much time to work on a lab report anyway. So just going to make it Saturday. And I don't want to, then on Sunday you're preparing for whatever's coming up in the following. I want you to have the lab done by then. So you have Sunday to figure out what you need to do for the next week. So that's my rationale. We want one report per team. I expect and have received almost always good grammar in your reports. I want you to state the objective. I want you to state the results, images when possible, and they must be high quality. We aren't, we aren't allowing anything like hand-drawn stuff and all that. There's too much out there now that you can use to create any kind of image that you want. Tables when you can't use images or graphs. A discussion of your results. It should be thorough, and it should treat if you have unexpected data, because these are labs, right? Just like any other lab, we know what the answer should be almost always. In a lab, that's the way it is. And if you get some unexpected data, you gotta treat it. I mean, you gotta call it out and say, well, here it is, and here's why we think why it might have occurred. Okay, for the lab reports, I'm just going to recommend a format. It's pretty open, but this is something like what I would like to see, something along this line. What's wrong with this picture? Obviously, this is an old picture. We have a monochrome oscilloscope figure here. But the FFT plot, there is an FFT plot in there. If you look closely enough, you can see it. It's obscured by the sine wave. That's not the way to do it. You take the upper half for the waveform and the lower half for the FFT or vice versa or something like that. The monochrome obviously makes it worse, which is something you won't need to worry about because you will have full color on any oscilloscope stuff that you'll be using. One of the worst things about this is that there is no scaling here for the FFT. So even if you had the peak out there nice and visible, there they are, there are a couple of peaks, you have no idea what the frequency is. There's no data on here to help the reader understand where those peaks are. So that's a problem. You've got to be able to decipher and get an understanding of whatever you're showing in your figures. And the figures, of course, what are they there for? They are to buttress something that you have said in the text. So that's what they're there for. You can't just put the figure in there and assume that the reader will be able to glean what you meant by putting that picture in there. You've got to have words in the report, and the picture is there for support. It's a support device. Okay, so here's a caption for the figure. The caption is, you can see that the caption for this figure is up here. There it is right there. The caption, this thing down here is the caption for a figure on the next page. Don't do that. Make sure that the caption and the figure are on the same page. At least they got the figures correct. They got the waveform here and the FFT plot here. Good. That part's good. That part is good. So you can use a page break always to force the caption over to the next page. Here's another no-no. Don't do this. What have you got? You've got a table that starts on one page and ends on the next page. This is not good. Make sure that you format your report so that your tables and your graphs and your, everything is on the same page. Get it all there, It's almost always doable. You can almost always figure out a way to do it. If you can't, then you got to, if it's too big or whatever, you got to split the table up, or do something. Do something. Okay, so grading percentages. So you can see here that, if you take a look at all the numbers in here, they add up to 100. The project obviously gets half of your grade. And it's made up of these items, which are over here. So the presentation, the milestones, the demonstration, these kinds of things. Personal performance, I'll talk about that. And here are the blogs. So the blogs are going to be 15% of your grade. So it's significant. It's significant. Okay, let's see here. So let's talk about personal performance here for a moment. A couple of moments. I'm going to make a couple of assertions here. First one is that very few engineers in today's world can be effective without having some programming chops. You got to be able to write code, decent code. It's about just about any engineer. You got to be able to do that. My second assertion is that much of DSP in today's world is moving from the big computer in the sky to embedded devices. And if I do this right, now let's try this here. I think I have to go back to pointer here. If I automatic hidden arrow, maybe okay. Let's see here. Let's see if I click on it, what happens? Nothing. Okay. I've got to, let's see here, I think. All right. So this is from the University of California. sister university, San Francisco, UCSF. No undergrad at UCSF, and it's mostly medical. So here is an example of the kind of thing that is happening now. Smartphones may help detect diabetes. That means that you're using the sensors that are on the phone, and you are taking that data in, and it is being treated on the phone. This is something, especially this medical stuff. There's such privacy laws and everything else. They cannot afford to ship that up to some big computer in the sky, have it processed there and brought back down. It's going to be done on the device. So you're going to see a lot of this kind of stuff happening in embedded systems. And all the IoT things that you can imagine, there's going to be a lot of pressure to have all of the processing, or as much as possible, on the device, rather than having to transmit it up, have it processed and sent back down. So that's what's happening. It's moving that way, very much so. So anyway, I just wanted you to see that. Let's see if I can get back now to my PowerPoint. Okay, and then here is a YouTube thing. If I go here and I go to, let's see, I think it's just about, if I go out to just about 1 minute. This is a MATLAB presentation. And so now I'm going to play this.
And how MATLAB can greatly accelerate the algorithm design workflow for these problems. We are also seeing a growing industry trend in pushing machine learning algorithms along with signal processing onto embedded devices and closer to the actual signal sensors. Here, I'll refer to the class of applications as sensor data analytics or embedded analytics.
There you go. This is, somebody that has their pulse on what is actually being done out there. And I offer this as another justification for not doing your AI project. If you're going to do one, not doing it on a big computer in the sky. There will be some kinds of things where you don't need to have it in an embedded system, but there's going to be an awful lot where you will. So that's why we're teaching with an embedded system in this course. We're teaching that because it appears that that's the way the world is going for an awful lot of stuff. Obviously, if you're going to be doing something like, maybe, nodule detection in an image from an X-ray or something like that, there isn't that much call for doing that in an embedded device. But, a lot of the things where you would be doing it on a large computer in the sky, you take it to a lot of developing countries in this world, and they don't have access to that kind of thing, and they need things where they will work on a low power handheld device that they can take with them into these places where they just don't have the resources that we have. So that's my rationale for maintaining embedded systems in this course. It doesn't mean that you must do it, but I really, really want you to do it. And all of our introductory stuff and training is going to be on how to use an embedded device. Okay, assertion number 3. It's better to commit naive mistakes in an undergrad environment than in your first job. So if you're not that much of a programmer and you're going to stay in the course, you're going to have to do some programming and you're going to make some mistakes. It's okay. It's okay. You're in a university here. We don't expect you to be, up to speed 100% on the things that you're here to learn, right? So do it here. Do it here. Okay. Those are my assertions. Here are my conclusions from those assertions. First, you will need to develop programming chops, or you will limit your potential in this field. You're in this course because you chose a signals and systems set of courses in your career, in your journey through UCLA here. I'm telling you, what I'm telling you is that in this one, in this particular area, you really need to be able to write code. Okay, and the second conclusion is that this course will have a lot of DSP programming with an embedded device. And it's not an Arduino. It's not Arduino Easy. This is a real device with a real development environment. And there are complexities, but they are the kinds of complexities that you will encounter if you are going to do this kind of work in a job. So embrace it. Or maybe, and you perfectly, permissible, you decide that this is not what you want. I totally respect that. And, and I wish you the best of luck. So anyway, but if this is not what you want, I don't want you hanging around the course, this is not, you really need to take the design course that fits where you want to be. Okay. So, all team members, I expect them to contribute equally. And equal contribution is that each member does some coding. And each member writes part of the report. It is not that one person runs the experiment and the codes and stuff like that, and the other person does the research and writes the report. That's not contributing equally. There are places where that kind of division of labor makes a lot of sense, but this is not one of those places. I expect you all to be able to code some when you get out of this course. I just have to remember several years ago I got a comment in the evaluation at the end, and the guy was really upset of all the coding that had to be done, and and one of the ending comment was, "For your information, I am not a computer science major." I get it. I get it. Just because you're not a computer science major doesn't mean that you can avoid writing code. Okay. Equal contribution is required for experiments, mini projects, and the project, and grades could be affected and one way is that on the blogs, because you will be writing individual blogs where you talk about what you personally have done. The word "we" in these blogs should be highly outnumbered by the word "I." That's what I'm looking for. I'm looking for what you individually did in this course, in that week, because it's going to be a weekly blog that I will be reading and the TAs will be reading. Keeps us up to date as to where you are. It's been pretty successful. So Jawei will be setting up a Wix site for your blogs. Okay, so if you are unsure of your ability to perform well in this course, please talk to your TA or talk to me. We'll work something out. And maybe the workaround or the workout would be that you drop the course. That may be the best thing for everybody. And, like I said, I will certainly respect that. That is, we have to be, reasonably rational about this stuff. So, okay. Enough of that. Oh, okay, we still got some more, just a little bit. Plagiarism, we have seen it in this class. If we see it, we're going to report it. I'm duty bound to tell you that. Cooperation, on the other hand, now trading ideas is fine, and I encourage it. It's fine if you sit down and talk about how you're going to do something with another team or how they did it or whatever. That's great. Trading code, now that's not fine. You're expected to generate your own code. Okay. That is it. Okay. So, I will stop here for a little bit, and I'm going to end this video.